It's for many of you might be one of your last lectures for your undergraduate, so congratulations. Can't believe that. So those of you who are going to be coming back for your master's degree, you should be signing up for autonomous vehicles. Sign up too. You're not done yet, but this is a milestone nonetheless. So some of you guys might have classes tomorrow, in which case, well, it's not your last class, so I apologize. But that being said, I hope you guys have learned a lot as we move through this semester. What this class embraces has been a lot. I mean, if you think back to where we started, dealing with spatial representation and what a point was in space, and here we are talking about what we're talking about, and you guys look at the robot arms that you guys have constructed, you guys have come a long way. So I think that journey's been a well worth journey, but a journey nonetheless that is definitely something you should be talking about to future employers. So because it embodies so many different aspects. So today what we're going to talk about the last topic. Our topic is going to be, we're finishing up the discussion on the idea of paths and trajectories. And so what we'll do today is, in a second, just close this down. What we're going to talk about is the idea of blending a robot arm, or the trajectory from a robot arm. And so, as we saw before, we can do a very high order polynomial. You saw the effect of what it does by looking at that MATLAB simulation. I just realized I forgot to post for you guys. I have to write a note to myself. So I got half of what I'm supposed to get done, but I just realized I didn't get all of what I'm supposed to get done. So let me write a note. Suppose I can do it on my phone. All right. I will text myself. All right, so we want to do post homework problem. Post the solutions for the homework for chapter 7. And we want to do is post the sims, the MATLAB sims. Okay. Anything else I can remember, I'll do. Okay, so we have these blended trajectories we were talking about. So we could go from a high order polynomial, and the idea is really, it's that airplane, right? So we're taking off, and all of a sudden, where we have to have a lot of detailed motion information, we're at a high order polynomial. But then we get to that cruising level, and there's no reason to have a 7th order controller. I mean, that just, or 5th order controller, that just gets excessive. Because it's basically constant. We want to be able to control accelerations, so we're probably going to measure intervals. So we have a 3rd order motion at the most. We're traveling along here at a constant velocity, and then we're going to come in for that landing. And that again, because we have to control these higher order motions, we need to have that higher order motion trajectory profile. And that's really what it's all about. The very beginning of the semester, we talked about, if you remember, we introduced this class through the controls perspective. And we're going to finish on the controls perspective. Because at the end of the day, we need to control the motor velocities. In controls class, almost the same shirt, but it wasn't quite.
We were just at the awards dinner, or award luncheon.
I know, I had another lunch already. I know. Did you guys go?
I did, yeah.
I had a meeting.
You didn't miss much, man. It was not very exciting. There was like 3 seconds of speeches, and then it was issued.
What was food?
Some pretty rubbery chicken, cod, red potatoes, some gnocchi with asparagus and peas that was really bad. So dessert was great though. Chocolate cake was to die for.
My lunch goes back, I can tell you that. So we started this semester with controls. We're going to finish on controls. And so, we want to control the velocities. The velocity is everything, as you guys have now realized. It defines the entire robot, right? We did talk about the motions, the fixed angles, theta 1 to theta 2 and then transforms. But to get from theta 1 to theta 2, we have to have a theta dot. To get to a theta dot, we have to have theta double dot, and theta triple dot, and so on, which is where we are today. But to avoid this idea of this really high order polynomial up to maybe a fifth order, and we could go to a seventh, we can be a little smarter than that. And so the idea behind being smarter is that we can do something that looks like this. Were a lot of people at the award ceremony?
Yeah.
Yeah?
I think there was 60 to 70.
Okay. Mostly faculty, I'm assuming?
Oh, yeah, 95%.
Yeah, when we didn't have a department meeting, I planned another meeting. All right, so, suppose we're starting off at some theta initial, right? So here's our theta initial, and we want to get to some theta final like we had before. So here's theta final. And again, this could be 75 degrees or whatever we want. This could say start at 30 degrees. It doesn't really matter. Something like that. What we see is, we're going to have the positional profile, and it might look something like this. And through these various regions, what we're going to have let me go ahead and make this one a little bit more pronounced just for it to make the point. I'm wondering if I need to get a new tablet or just reinstall everything. Whereas Windows just getting too excessive. This is Windows 10.
Bloatware.
What's that?
Bloatware.
Yeah, I'm kind of wondering that. So here is, say, our inflection point that we're going to have right here. And we could call this, we're just going to call this point T. And we're going to call this point right here TB. And so we're going to look at this time right here as TB. So what this is going to be known as is what we're going to call our blend time. And then we might see another aspect over here, which is also going to be a blend time, but now it's going to be T final minus the blend, TB. Come on, stupid. Okay. And then this is going to be our final time. Right? And so again, we know we have a trajectory because we have time, right? So it's just time t initial or time t0. We can say t0 or ti. And in this region, we could have a fifth order. Okay. Here, we could do a third order. And then here we could have a fifth order. And so during the traversal, this is, we could consider this to maybe be more of a parabolic. This could also be linear and another parabolic. Even though it's parabolic, we're going to take it to a fifth order, so we have very good control. Now, in reality, I could also have done all of this, right? I could have done all of this here as, say, a seventh order, if I wanted to. But again, that can get a little excessive. And so, instead of doing that higher order, much higher order, I can limit myself to maybe be nothing more than a fifth order. And if I go to a fifth order, then that means this is going to have a region where I have a set of coefficients, say from A0 down to A5. Then I have coefficients, so these are going to be my coefficients. And then I'm going to have a coefficient set, which is going to be from, say, B0 to B2. And then here I have a set of coefficients, which we're going to call say C0 to C. So each segment will have its own set of coefficients. Okay. This duration is going to be TB, and this could be TB as well. And so this T right here, we really see it's kind of like having that nice linear region that we have going on. But we have to recognize that as it kind of blends together, what's going to happen is we're going to have, let's go to that one here. Coming into this segment, we carry the velocity and the acceleration. I'm going to say it's a deceleration, I know that, but I'm still going to call it acceleration from segment 1 into segment 2 initial conditions. So you remember before when we were doing V initial was 0? V initial is not 0 anymore. It's going to be what we ended right here. So, for example, V final from segment A, or segment 1, becomes V initial, in fact, I'm going to call it theta dot, becomes theta dot initial for segment B. And theta dot final from segment B becomes theta dot initial for segment C. And I'm using A, B, and C only because, let's go ahead and say we have segment A, segment B, segment C. Because we use the coefficients A, B, and C. So let's just call them segments, A, segment B, segment C. So we're decomposing this large trajectory into some key regions as we traverse from one location to the next. And we can also, by doing that, we know what this particular theta is. We know, let me review this and how that theta final. We know what this, boy, this thing is super laggy. I rebooted it just before class. It won't let me erase. We'll just scroll down. So let's call it 75 degrees. So there's some theta here, and we could call this theta A to B, and this could be theta B to C, for example. We can label it whatever we want. And we can actually calculate what that's going to be. Right, so this is theta initial. Because once we create this profile, we can create that equation, that fifth order equation. We know how much time we want to have that for, or we could say, let's solve for a theta and find out, or let's set the theta and solve for the time. We can do either one of those two relationships. It's very trivial at that point. So we can go through and solve for either one of those and then know where we want to be at. But what we do need to do as we define the segment regions, we need to ensure that we have ample time. So, for example, TB has to be less than or equal to at least 1/2 of our time final. In other words, we can't say that our blend is greater than half of that, so we run out of time space. Okay, does that make sense? So the idea here is TB has to be at least half of TF. It can't be greater than TF. Half of TF, I should say. Make sense on that one so far? It's just a constraint. Otherwise, we run out, right? So we're coming out of here, and the other one's starting to end. We never ever actually had the proper blending. The idea is, as we go through this region, we're making those smooth transitions at that blend point in time, which translates to a blend point in space. So far, so good? And so, we can look at this, say, a second order, say theta t. We can write that as C naught plus C1t plus C2 squared. And clearly theta dot of t becomes C1t plus 2 C2. And of course, double dot of t is nothing more than 2 C2. And so if we look at theta, that final position theta is going to be equal to that blend location plus some theta A minus theta initial. So the question we have to ask ourselves in this theta dot final is going to be 0 at the end. At the end, we want it to stop. And so we have to ask ourselves this question is for a second order system. How much ramping do we use? So if I have a second order, then how do I solve that answer? How do I answer that question? How do I determine how much ramping I use? This will be questions that you're going to have to do the analysis for on your exam, which is take home. But I'm going to ask you the question now. How do we determine how much ramping we use? Just for a second order.
It's 0, right? Like it's predetermined?
Well, no, it's very determined. In fact, we spent an entire chapter determining it.
Oh.
So what determines how much ramping we use? Essentially the acceleration or the force or the torque requirements, right? All of them go hand in hand. Torque is proportional, force is proportional to torque is proportional to current, right? One's got a moment RML, the other one happens to have the coefficient of KT. K, depending on how you look at it, which K you're looking at, but some coefficient, which relates the magnetic field or the magnetic flux of the motor, right? That's what sets the torque of that motor. It's I cross B. What's B?
Magnetic field.
Magnetic. Well, what is it for that motor?
Oh.
That's what sets this, how much ramping do you use. Because if you have too much ramping, or if it's too steep, you don't have enough current to drive that, right? Or you don't have enough torque to get what you need out of that motor. And you fail. What could happen if you try to do that in the real world? If my torque requirement exceeds what I'm asking of it, what happens to my motor? It stalls. Okay, if it stalls, then what happens? If I try to keep driving it once it's stalled, then what happens? It goes poof, right? Because now all of a sudden, I got all this heat pouring into it, and all that heat, it's no longer, none of that energy is now motion, it's all heat. It's all I squared R, and I squared R, and then R has only so much, it turns into basically a heater, but it can't absorb that much thermal material, that much thermal energy for that duration. The wires heat up and they burn out, literally burn out. So it's important that we understand this. And this is the reason why that's why we spent the analysis of the Lagrange understanding those force relationships, which are really driven by the accelerations. Remember Lagrange had accelerations, right? It had the different types of accelerations, right? Which one was the first one? It's in my notes, I don't have to worry, I have it memorized. Right, I had just the accelerations, right? And then I had centripetal, Coriolis, and gravity. Right, I had my energies. Because I need to understand this. We could have done Newtonian, but Newtonian gets rather complicated very quickly for that much joints. So really what we're saying here, if I look at it from a theta dot perspective, again, just a simple second order. We just talked about the nth order, or how to do the blended. But what we're talking about here, and this is what you guys might be doing even in the lab, the idea is this is going to be our blend time. This is constant velocity. And this is another blend time. TB may be TB1 and TB2. TB1 does not necessarily have to equal that means they can be an asymmetrical motion profile. Most of the time it's not, but it does have to. So in other words, TB right here, we can't, if TB is beyond half of T, right, I got my funnel T right here, I haven't finished ramping. So in other words, if I set my ramp time to be here, I'm ramping here, I may not have enough, in fact, I may never even finish, I may never get to a constant velocity. So we have to make sure that all of this is doable. So when we say how long it takes for something to go, remember what defines the trajectory? Time. If so we say it has to be this time, and it's just too steep, we can't do that. So our velocity, our final velocity has to be doable in order to make things happen. Does that make sense? What drives that motor joint velocity? Do I just pick it? No. So how do we find theta 1 dot? Theta dot 1. And theta dot 2, theta dot 3, theta dot 4.
You're doing the whole semester?
So what technique did we use to do that?
IK solver or like?
Well, you're on the right track, right? So it's really defining that end effector velocity, right? That end effector velocity drives the individual joint velocities, don't they? And how did we relate this end effector velocity to the joint velocities? Nope. Not the accordion, but the Jacobian.
Oh.
The Jacobian says end effector velocity path, this is what I want. And I can go backwards through the inverse Jacobian to know what the theta dots need to be. So there's my velocity. That's what's defining this parameter right here. But I can't just instantaneously get to that parameter. Kinematics fail the analysis when I have a load. The load is driven by the mass and the length of the arm, hence that's still part of the load. So that's why we covered Lagrange. But as you saw, Lagrange is very much a cookbook approach once we got through the minutiae, right? It's just kind of like turning the crank at that point. What we're driven, the engineering comes from here, understanding this. The Lagrange is simply a tool where we do the analysis. And we knew how to go from point 1 to point 2 because we understood the transform space. And I think you begin to see all of this start coming together, right? We've been talking about individual things, but this particular chapter brings it all back to where we started. And that was actually the control of the velocity. And now you see why I introduced the topic of robotics as the control of the velocity. You all see that now? So, if I look at it from a second order system, just as an example, from a second order perspective, I can define the time TB to be the rotational velocity omega over 2, which I can then say delta of theta plus some omega TF over omega, which equals, I can rewrite this as theta initial minus theta final, plus that rotational rate omega times TF. So remember, this is how far I'm going to get, right? This is my change of these two guys. You could consider this to be a theta dot if you wanted to. I know dot there's. That's weird. And so we can say that TB, that's under omega. So TB, or where TB, is less than or equal to T initial minus T final over 2. Right? So we can look at this to be like, say, our delta T. So these are just some constraints, and this is for a second order. So we can be asking ourselves, what is that time? And I can extend this beyond that second order idea and say, well, if it's a fourth or a fifth order, it doesn't really matter. These relationships of theta still hold true. This diagram that we have right here is still true. And so what we're doing here is we can approximate, or by performing blending, much higher order polynomials. Maybe like a 7th order, or even a 9th order. And yeah, I didn't say 9th order. Could you imagine a 9th order motion profile polynomial? But you can justify easily the 5th, couldn't you? We just did. We could say, okay, and I can even see a 7th if I really had to have precision motion. And so what I could do is I can blend these into, say, what's called a 4-3-4, or even a 5-3-4. I'm sorry, 5-3-5. I could do a 5-3-4 if I wanted to, I suppose. I mean, the book doesn't give that as an example, but I could do a 5-3-4 if I wanted. Doesn't really matter. And so we have basically 3 segments of the trajectory. We start and stop. We can start and stop with the 5th order, and then so we can say we can start and stop with a 5th order, where the majority of the motion is a 3rd order. If I think about this from a controls perspective, then, I mean, controlling a 7th order polynomial motion, that controls have a lot of really weird harmonics, it turns out. So if I could limit the amount of high order controls, then I can limit the amount of interactions going on, dealing with the lower order controller until I need to have a higher order controller. And so if I look at, say, for example, we have a 4-3-4. My segment 1 or segment A. Let's just call it segment A. Could look something like this. So our theta A of t is going to be A naught plus A1 t plus A2 t squared, t squared plus A3 t cubed plus A4 t5 plus, I'm sorry, forgot. There we go. Right, and then this could be like, say, the acceleration phase, and then my travel phase could be segment B or segment 2, where theta B obviously is nothing more than A naught, so B naught, plus B1 t plus B2 t squared. Okay. And my G cell, and I could, if I wanted to do a B3, I could do a, that's a 4-3-4. Let's just leave it at that. In my segment C, or theta C, would be C naught plus C1t plus C2t squared plus C3 t cubed plus C4t. And just like we found all of the coefficients in the very beginning, we do the same process, but we do it 3 times, but we don't have to go to a 5th order. In this case, we're only going to a 4th order. So we really just rinse and repeat, where we have the initial conditions from the one driving, the final conditions of the one driving the initial conditions of the next. Does that make sense? We've already done that problem once already. So in the book, there's like 12 steps. There's 12-step solution to doing this. I could write it out, but I think in all honesty, it's faster if we just read it and just look at it. I remember where I stuck the Niku to look at. So here we are. The 14, or depending on how you look at it, 12 different steps. So we know the initial condition, we know the initial velocity, we know the initial acceleration, or it's given to us, or it's determined from the physical system. Then what we do, in fact, there's a better thing. Here we go. So in this case, we're going to do a 4-3-4. We can do a 5-3-5. And so we use our initial conditions to arrive at A0, A1, and A2, just like we did before. Then we compute our theta 2 as a function of our final time. So if we said, we know what our initial theta 1 is, or initial theta 2 is, it's our final position of theta 1. Our final position of theta 1 is given that fourth order polynomial for the duration of that segment of that first segment. So if we broke it down, suppose we said we have 9 seconds to travel from point initial to point final. We're going to do a 1.5 second acceleration, 6 seconds of travel, and then a 1.5 seconds of deceleration. When I get done right here, this would say, okay, where am I at after my first 1.5 seconds? I put that in there. After we solve